This is the fourth lecture of week 6, and we're going to cover model specification. So what we mean by model specification is selecting variables to include in the regression model. So the first step in this model specification is identifying the variable of interest. Asking yourself what is the causal relationship that you're interested in. The second step is to think about if there's any potential omitted variable bias. So are there any factors that are missing and that satisfies the two conditions of omitted variable bias? The third step is to include these potential omitted variable factor in your model if you can. And if you cannot include the variable directly, then include another variable that is correlated with the omitted variable to serve as a control variable. And control variable is effective if once they're included, the omitted variable bias no longer exists. So this model would be called a base model or benchmark model. The next step is to come up with alternative models where other candidate variables are included. And then you estimate your baseline model as well as your other alternative models. And we call this sensitivity checks. So when you're doing sensitivity checks, you're checking if your variable of interest coefficient or coefficient of interest changes a lot when you include these additional variables. You also want to check if these additional variables in the model are statistically significant. One thing to note is that you shouldn't just focus on maximizing R-square. R-square is important, but your decision to choose one model over the other shouldn't be only focused on R-square. Let me give you a few reasons why you shouldn't just focus on maximizing R-square or adjusted R-square when choosing the best model. So the first is that a high R-square or adjusted R-square doesn't mean that you have an appropriate set of regressors. Just like when you have a low R-square or adjusted R-square, it doesn't mean that you have inappropriate set of regressors. Which regressors to include in the model should be dependent on what type of data you have and your expert knowledge of the model or the problem and the data quality. Choosing the right regressor is a complicated problem and there is no right answer. And a lot of these decisions may be subjective and sometimes it depends on your expert knowledge. The second is that high R-square does not mean that you eliminated omitted variable bias. So omitted variable bias can exist when you have high R-square, as well as low R-square. So just because you have a high R-square does not mean that you have eliminated omitted variable bias. The third thing is that a high R-square does not mean that you have an unbiased estimator of a causal effect. So imagine a case when you have test score as a dependent variable and the number of parking lot as an independent variable. In this case, you may have a high R-square because they are highly correlated. You can imagine school districts with large number of parking lots may have low test scores. But just because this model has a high R-square doesn't mean that number of parking lots somehow causes the test score. So in this case, the high R-square does not necessarily mean that you have unbiased estimator of a causal effect. The last thing is that the high R-square does not mean that whatever variable that you're including is statistically significant. So in order to determine whether a variable that you're including is statistically significant or not, you need to conduct a hypothesis testing using the t-statistics to reject a null or not. And you shouldn't just look at if the R-square is increasing or not to determine whether a variable that you're including is statistically significant. For example, if you had a model that included only STR in our test score example, and another model that included STR and the percent English learners, and the R-square increases in the second model, that doesn't mean that the percent English learner is statistically significant. You need to test this using the test statistics to determine whether the percent English learner variable is statistically significant or not. Let's go back to analyzing our test score data set. The first step in model specification is to identify the variable of interest. So in this case, since we're interested in the student-teacher ratio and its impact on test score, our variable of interest would be student-to-teacher ratio. The second step is to think of potential omitted causal factors that could result in omitted variable bias. We believe that the percentage of students who know English, outside learning opportunities, parental involvement, teacher qualities can all be correlated with student-teacher ratio and have a direct impact on test score. So these are all the variables that can potentially cause omitted variable bias. So once you have identified the omitted factors, then you can either include these omitted variables directly in the model, or you can include the control variables that are correlated with the omitted variable that you cannot measure. So in our case, you can directly measure the percentage of English learners. So we can include this variable in the regression model directly. But in the case of omitted variables such as outside learning opportunities for students, parental involvement, and teacher quality, these variables are hard to measure, so we need to include a control variable that is correlated with these omitted variables. And in our case, we can include a variable that measures the wealth of the school district as a control variable instead of the omitted variables that we cannot measure. So the next step is to consider other alternative specifications. So in our case, we said our control variable would measure the district's wealth, and we proposed two different measures. So the first is the percentage of students who are eligible for subsidized school lunch, and the second variable is the percentage of students who are qualified for income assistance. We don't really know which of these measures are better at controlling for the omitted variables that we cannot directly measure. So what we're going to do in our alternative specification is that we're going to include these variables one at a time and also include both at the same time in the model. In this scatter plot, you can see that the three variables that we want to include in the model are all negatively correlated with the test scores. So the percentage of English learners, percentage of students who are qualified for reduced lunch, and the percentage of students who qualify for income assistance are all negatively correlated with the test scores. So once you have estimated the regression models, what would be the best way to present the information? In previous lectures, we have presented the regression results in an equation form, where we wrote the coefficients. For instance, 536 is equal to 234 times student-teacher ratio plus some number with the standard error in parentheses underneath. But this is probably not the best way to present the regression results when you have multiple regression models. So the best way would be to present the information in a table format, which includes the coefficients, standard errors, and other important information. So here's a standardized table that is often used to present the regression results. Usually the regression coefficients are presented first, and the standard errors are presented in parentheses underneath the coefficients. And each column represents one regression. So in this case, we have 5 different regression models. The table usually includes at least the adjusted R-squared or R-squared and number of observations. The table often includes these stars to indicate the statistical significance. So in this case, 1 star represents that the coefficient is statistically significant at 5% level, and 2 star represent that it's significant at 1% level. So let's look at the regression outputs. The first thing to note is that our baseline model to the model, when you include the percentage of English learner, the coefficient of our interest decreases by 1/2, meaning that our baseline model of only including student-teacher ratio probably suffers from omitted variable bias. Another thing to note is that the student-teacher ratio alone doesn't explain the variation in test score very much, as you can see from the adjusted R-squared. The adjusted R-squared for this very simple model with only student-teacher ratio is 0.05. Whereas once you include the percentage of English learner, the R-squared increases significantly to 0.42. So the model where student-teacher ratio is only included as a regressor doesn't seem to explain the test score very much. The second thing is that whether you include what type of control variables, our main coefficient of interest doesn't seem to change that much. They're all hovering around -1, and they're all statistically significant, at least at 5% level. This -1 means that when the student-to-teacher ratio decreases by 1, then the test score would increase by approximately 1. Also, you notice that if you look at the sign for the control variables, they're all negative, which is consistent with the scatter plot that we saw in the previous slide. And the last thing to note is that the percentage of students who are on public income assistance seems to be redundant, because once you compare Model 3 and Model 5, you can see that the coefficient of interest so student-teacher ratio coefficient doesn't really change even when you include the percentage of students who are on public income assistance program. And in addition, adjusted R-squared also remains constant, meaning that the percent of public income assistance doesn't seem to add that much to the model, so it seems redundant. So to summarize, multiple regression allows you to estimate the effect of X on Y, holding other variables constant. And sometimes you may have an omitted variable bias. So in that case, you can include the omitted variable. But if you cannot include the omitted variable directly, then you can include a control variable that is correlated with the omitted variable. There is no simple way to decide which variables should be included in the model. A lot of it is very subjective. And lastly, one way to deal with this issue is exploring different models and seeing what happens to the the main coefficient of interest.